I'm here today to talk about the AW control system from Schmelzer. Schmelzer as a company have long been renowned as specialists in storage ventilation of all combinable crops. Established over 100 years ago, their origins lie not just in the innovative ventilation hardware which they manufacture, but also in the complex science embracing the properties of air and water. They knew that to master metal in the production of high-quality fans, ventilation floors, grain transfer systems, and so much more was only part of the story, and that to master air and water was a vital key in completing this complex picture. 5 years in development, the Schmelzer AW control system is ready to become a market leader in automatic storage control. Hence the title at the top, Wasser ist nicht gleich Wasser, which is, in English, water is not simply water. The second slide is an index divided into 3 main columns, entitled Introduction, AW Basics, and AW Control Operation. In column 1, slide 3 expands a little on the customer perspective and what key players in agriculture expect from a good control system. Slides 4 to 10 cover the relationship between the elements which affect the rise and fall of storage problems and why the term AW is so important. The second column, AW Basics, introduces the system, its components, and how it all works. And the third column, AW Control Operation, shows how to install and operate the system, highlighting the strengths of the system and areas to avoid and essential good housekeeping. So on to slide 3, customer perspective. What should we demand from a good grain store control system? Increased farm efficiency, earliest possible warnings of potential threats, reduction in running costs, energy and labour saving, ease and flexibility of use, high level of confidence in the system, in other words, peace of mind, must be better than existing systems. That's why monitoring of AW is such an important step forwards. Assurance of crop quality and traceability. Must be compatible for integration with other precision farm data systems. The bigger picture. Increased focus on environmental considerations. In slide 4, we describe the basics of AW using a simple cross-section of a grain of wheat. It's easy to assume that if the moisture content of grain is reduced, then the water available for the microorganisms will also be reduced, but that is not always the case. It's not only the pure water content in the store which is important, but to what extent that water is bound through the substrate of each grain, and how temperature affects the mobility of that water. This water activity affects the growth of microorganisms, chemical processes like fat oxidation, non-enzymic browning, the activity of enzymes themselves, and also, sometimes overlooked, the physical characteristics of the grain itself. The availability of water for physical, chemical, microbial and enzymic processes is described as water activity, more commonly known as the AW value. In scientific terms, the physical definition of water activity is the ratio of the water vapor pressure of the grain surface to the saturation vapor pressure of pure water. In practical terms, water activity is a measure of the available water in or around a material, for example, a grain of wheat. Water activity is temperature dependent. Therefore, an increase in temperature increases the mobility of water, which means that water migrates from areas of high AW to areas of low AW. Two identical grains can have the same overall moisture content, but can still have quite different AW values. As a general rule, as this chart shows, virtually no microorganisms grow below an AW value of 0.6. And so typically within a controlled storage environment, an AW limit to aim for is 0.65. So in slide 6, we ask the question, why do we measure the temperature, the AW value, and the intake of air humidity? Many automatic systems don't react soon enough because they rely principally on incoming ambient conditions, humidity, of course, and temperature fluctuations in the grain itself, and not necessarily moisture. Critically, this leaves greater time for problems to build up in the store, which are then more difficult to reverse. This chart demonstrates that growth of microorganisms can start to increase some time before temperature thresholds are reached. This may only be a matter of days, but can have a long-term effect on returns. Every producer of a food commodity knows that quality commands a premium. The ability to store and maintain that quality over long periods is vital to maximizing returns. This chart clearly shows that higher AW values will invariably reduce germination percentage over a shorter timescale. We see the higher AW value of 0.75 at 15.5% moisture, represented by the blue points, would struggle to maintain germination percentage and therefore saleable quality for much longer than 2 to 3 months. The mid-range, marked by the yellow points with a target AW value of 0.67 and 14% moisture, shows more resilience in longer-term storage time, only beginning to tail off after around 12 months. The example shown by the orange points at the top of the chart with an AW of 0.33 and moisture of 9.5% indicates the best possible outcome when a producer is looking to protect their investment long-term with confidence. Of course, to maintain these levels over long periods can only be achieved with a really good system, but it doesn't necessarily mean a costly long-term cooling operation. When it comes to cost control, timing is everything. This chart, courtesy of Mühlbauer's highly acclaimed Handbook of Grain Drying, reinforces how different combinations of temperature and AW values can be converted into a rise in grain moisture without any additional external influence of humidity. Water migrates from areas of high AW to areas of low AW, never the reverse. So the intake of ambient air with high relative humidity must be prevented in order to avoid an increase in the AW value. And this is where highly sensitive fan control with preset parameters becomes so important. This is also why the Schmelzer AW control system becomes such a valuable tool in the store manager's determination to maintain good grain quality over long storage periods. So having outlined some of the background to the AW approach of good long-term grain storage, we can look at a schematic overview of the system itself. The grain store shown here is set up with a network of ventilation ducts and corresponding fans. Each fan is individually controlled, and unless they are overridden manually, will only respond to the information transferred to them by the data collection box. The information is sent to the data collection box from the network of sensors which are monitoring grain conditions at varying depths and at strategic intervals wherever required. This slide shows the complete overview of the AW control system, which highlights the data collection box as the central element or hub of the whole system. It maintains multi-directional links between the measuring rods or sensors in the grain, Schmelzer fans with existing integrated reception systems, and of course the internet or server. All these functions are overseen remotely by the user with a smartphone, tablet or desktop connected by Wi-Fi or Ethernet cable. Of course, every store is different. Reliability of Wi-Fi is dependent on a host of factors, and this chart shows the potential influences on reduced reception. In an ideal situation, free field range, that is, without obstacles, is in the region of 200 meters. Attenuation or reduction of signal increases considerably wherever metal is part of the construction. For example, steel reinforced concrete or metal walls. This list of commonly used materials in construction is worth keeping in mind wherever setting up the system for the first time. If there are unavoidable obstacles in the path of a good signal, additional data collection boxes can be installed, and each of these then acts as a transmitter and receiver. The data collection box is shown here in more detail, with each of the main functions labelled. The unit consists of three main components: the pre-assembled unit itself, the DC power adapter, and, for safe mounting, the top hat rail. As with the previous slide, which emphasizes awareness of attenuation, it is also vital to avoid installing the box inside a metal cabinet or container. Dust is often a risk in storage environment, and when there is a need to protect the unit, then use a plastic container. Each function described here in the diagram is further explained in the detailed instructions on fitting and operating, which are included in the AW Control Operator's Manual. This is to demonstrate that the data collection box requires different settings for Wi-Fi or LAN. It's important to remember that when the control box is connected via LAN, that the DIP switch must be changed. More detail on this can also be found in the Operator's Manual. This describes the overview of the menu to set up the system. The straightforward configuration of 5 buttons to the top left of the unit enables the user to select letters, numbers and signs to input information such as the SSID or name of the network, the username and password, and other functions as required. This is basically a reference to the more detailed instructions in the Operator's Manual, and of course one-on-one guidance is available at all times. The data collection box would be without function if no information was being transmitted from the measuring heads, and here we begin to describe these in more detail. The heads are separate units which are rechargeable via a DC charging point, which is fitted with a protective dust cap. Each head has its own identity, which is displayed by the QR code and unique ID number. Once this unique identity is established in the system, it will monitor a specific area within the store and activate the corresponding fan when required. Remember that wherever that measuring unit is placed or repositioned in the store, it will continue to register that identity with the control box, even if the location has changed. And this is where a site plan locating where the sensors are becomes not just good practice, but also vital in avoiding errors. Here we see some general data on the measuring head. Of particular note is the battery life. Once it's fully charged, which takes around 24 hours, it will give up to 12 months of use depending on temperature in the store. Also bear in mind that the measuring head includes a 1 meter rod and sensor, and it can operate with as many as 6 additional rods with sensors. Each of the additional rods is a sensor in its own right and is therefore capable of retrieving data at intervals of 1 meter, which means that it's possible for a single surface-based measuring head to be receiving up to 7 measurements up to a 7-meter depth of crop. Here we see several measuring heads placed at regular intervals into the crop and ready to start receiving information. The position of the measuring rods should be decided at an early stage. Setting up is complete when a fan or fans is assigned to every measuring rod on the online platform. We show here the top and lower end of an extension rod and also a chart stating dimensions and tolerances. The process of linking each rod to the next is relatively straightforward, but the units themselves are highly sophisticated and should always be treated with respect. This slide shows a step-by-step process of attaching an additional rod and sensor to the measuring head. The conical section, or tip, is detached at the top of the next rod and clipped into place. This junction then retains its function as a sensor, and when the tip is replaced at the lower end of the next rod and pushed gently into the crop, it becomes the next sensor. You then have 2 measuring points, one at 1 meter and one at 2 meters. This process can be repeated up to a maximum of 7 measuring points. The conical section or tip has 2 main functions. It makes entry into the crop less stressful on the rods and also acts as protection for the final sensor. But worth noting here that although the theoretical maximum is 7 meters, Schmelzer do not recommend 7 sensors in every situation because of the physical differences between various crops. Oilseed rape, for example, because of the smaller grain size and round shape, offers considerably less resistance when pushing the rods into the crop. Barley grain, however, with its larger oval shape, requires greater force, and any depth below 4 meters may risk damage to the rods. The process of extracting the rods from the crop is just as important as inserting them. As these excellent pictures demonstrate, always detach each rod as it is clear of the top of the crop. Transport and storage in the original shipping boxes is the best way to protect them until they're needed again. Each of the fans listed here are specific to AW Control. They are already set up to receive instructions from the data control box, and they are assigned a unique article number. Obviously, the choice of fan depends largely on variables such as required air volume, air speed, depth of grain, total volume of grain, and the number of ducts being ventilated by a single fan. This, of course, serves to illustrate the importance of ensuring compatibility with each of the components of the whole system, including the ventilation and cooling process itself. And, as highlighted, particularly important to include a neutral conductor when installing these units. More detail on this and the fan specifications are included in the AW Control Manual. Not everyone using this new system needs necessarily to purchase a new fan. So if there is a need to recommission an existing fan, or if you want to connect and control another device by using the AW Control, you can purchase the fan control separately, as shown here. In this situation, it is extremely important that in order to avoid compromising the rest of the AW Control system, installation of this unit must be carried out by a qualified electrician and, of course, as with the data control box, always avoid steel housing. This is just one of many examples of a plan showing suggested positions of sensors in the store. The distance between sensors is shown as a minimum of 3 meters up to a maximum of 5 meters, and approximately 1 meter up to a maximum of 2 meters from the walls of the store. Here we see 2 medium to high capacity fans, each responsible for ventilating 4 10-metre ducts by means of exterior manifolds. Depending on individual needs, an alternative system could involve each duct being assigned to a smaller dedicated fan. The network of sensors would remain the same, with the advantage of a more surgical and economical approach to dealing with localized problem areas. As mentioned before, to work really well, a plan like this should not just include the pattern of sensors, but also, really important, to maintain their individual identity so that they can continue to monitor conditions wherever they happen to be located in the store. The automatic controls of the fans ensure that the conditioning of the grain is kept optimal at all times. This means that if the preset AW value is exceeded, the relevant fans switch on during a set runtime. There then follows a rest period of approximately 40 minutes, during which the AW value and temperature are measured. After this measurement period has ended, and the values are found to be still above the preset thresholds, the ventilation process recommences. If, however, the values fall below the threshold, those values are recorded every 15 minutes and sent to the server. Fans will not operate if the system is outside the preset operating time period, if the preset AW value threshold is not reached, human intervention, that is, if the fan has been switched off manually, and if the ambient conditions do not allow ventilation, that is, if the weather is too humid or too hot. This is a quick reference to trial online data access. By clicking on the link, a new potential user of the system can access test data or a trial account so that before going live in a real-time situation, they can become familiar with the system. Once set up, observe the operating instructions. There will of course be situations when the system may have to operate in remote areas without internet connection. This need not be a problem if you have a system using a mobile access point, such as the one shown here. This is a relatively inexpensive unit with low running costs, which allows the system to operate outside normal internet coverage. So, in conclusion, good automatic grain conditioning can minimize losses and maximize quality. It can also reduce high energy costs. With climate change in mind, this is a major challenge worldwide. And so we return to the opening phrase, water is not just water. The physical nature of water and how it changes in relation to location, temperature, and numerous other factors can never be underestimated. The Schmelzer AW Control System provides an excellent platform for advanced monitoring and maintenance of grain quality, and it is clearly an important step forward. Should you wish to learn more about this system and see it working in practice, Schmelzer offer the facility to log in to a test account where you can view an actual setup of the required components which are installed at one of Schmelzer's testing facilities. This sample setup can give a closer view of the advantages and simplicity of the online software without the need to create a live account and without the need to install hardware components on your site. Click on this link for more information. So finally, can we thank you for taking the time to view this video, and we look forward to hearing from you very soon.